Okay, test. I'm going to make a surprising statement here, and we'll see if we can verify it. The statement is that basically a polynomial function can be expressed entirely in terms of its derivatives at 0. And this is actually what's known in mathematical terms as a Maclaurin series. And let me show you what I mean. If I have a function f of x equals, say, I'll just call it a sub naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus dot dot dot, I can write the derivative of this as f prime of x is a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus dot dot dot, and f double prime of x is equal to 2a sub 2 plus 2 times 3a sub 3x plus dot dot dot. As a matter of fact, let's go ahead and extend these series out at least one more term. So this becomes a sub 4 x to the fourth, and this becomes 4a sub 4x cubed, and this becomes 3 times 4a sub 4x squared. Now, key to this statement here is that we're talking about the derivatives at 0. So if I said f of 0, I would simply have a sub naught f prime of 0 is equal to a sub 1, and f double prime of 0 would be 2a sub 2. Mainly because when I plug in those zeros, this a sub 1x is 0, a sub 2x squared, all of these x terms cancel out, leaving only that a sub naught. So basically, this just picks out that coefficient. If I continued on with this, I would see that f triple prime at 0 was 2 times 3, a sub 3, and f quadruple prime of 0 was 2 times 3 times 4. This 2 comes out, 2 times 3 times 4, a sub 4. So, in fact, each of these coefficients in the polynomial is associated with a single derivative of the function. Now, the Maclaurin series expansion of this, the Maclaurin series expansion is kind of the opposite of this. It goes the other direction. If I have a function f of x, then we can expand it. We can turn it into a polynomial, by calculating each of those terms, a0, a1, a2, a3, a4, and it comes out that it's going to be, basically we will take an index I equals 0 to infinity, and it will be the ith derivative of x times x to the I power divided by I factorial. So if I use that pattern, the 0th derivative of f of x would be just f of x times x to the 0 is just 1, and 0 factorial is also 1. So it'll be f of x plus, oh, I gotta make a modification here. This is supposed to be the ith derivative at 0. So, whoops. So let me erase that and put a 0 in there. F of 0 plus f prime of 0 x. 1 factorial is 1, so I don't need to write that. And then f double prime of 0 times x squared over 2 factorial, which is just 2. I'm going to scoot that over and continue, plus f triple prime of 0 times x cubed over 3 times 2, or 3 factorial. 3 factorial. So you can see the pattern continues along that way, plus dot dot dot. As an example, the sign, or let's start with the e to the x. That's a simple one. E to the x is equal to e to the 0, which is 1, plus the derivative of e to the 0 is also 1. The derivative of e to the x is e to the x. And then the next one would be derivative of e to the x is still e to the x, so it's 1 x squared over 2 plus x cubed over 6 plus dot dot dot. So let's look at how this matches. If I did e to the x, this is what the graph looks like from -3 to 3. Let's also go ahead and put in some polynomial expressions in here. Let's start with our zero order Maclaurin series approximation, which would just be this 1 without anything further. If I plug in that, you can see that we have a vertical line that just matches what the function is here at point 1, or at the 0 point. If I put in 1 plus x, I get a slightly better match because it matches from there to there, all the way along the tangent. Now if I add in plus x squared over 2, you can see it's even a better match still, matching almost from -1 to 1. And then I will go ahead and put in plus x to the 6th over 6, x to the 6th, divided by 6, and yet more range of where it matches. So the more terms you use, the longer the range on which this is accurate. Now the Maclaurin series for sine x and cosine x, and I'm going to be saying this is in radians. If I use radians, the Maclaurin series for sine x is x plus x cubed. I think, well, it's minus x minus x cubed over 6 plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. I'm sorry, these should alternate, minus, plus, and this last one should be minus. And it continues on that pattern. It actually has the same pattern of e to the x, taking every other term and swapping the minus signs each time. This time I would call the first one the first order, then the third order, then the fifth order, then the seventh order Maclaurin series expansion. So here is a plot of sine and its first order Maclaurin series approximation, which is x, this straight line here. So if I go ahead and put the third order one in there, x comma it was x plus x, no, it was x minus x cubed over 3 over 6. You can see the third order one gets closer to the sine wave. And then let's go ahead and take that one and add x to the 5th over 5 factorial plus, comma, plus x to the 5th over, I'm not sure how this thing does factorial 5, yeah. And did it get closer? Yeah, I think that. I'll go ahead and find factorial 3, 5, and 7 and just use the numbers. Okay, in any case, here we go. This is the first order expression. This grayish line here is the second order expression, or third order. And then from there we go out this blue one. Let's actually mark both of those three. And then this blue one, which is the fifth order. And fifth order. They all start high and go low, or start low and go high. So the fifth order, actually maybe the green one is the fifth order, and the blue one must be the seventh order. And you can see that with each new term, it gets just a little bit closer to this sine wave. But so all this is kind of answering the question of why we can use a complex number in here, and I want to explore that in the next video, what it means to put a complex number in an exponent. And we'll find what it does is it combines these this real part, which is exponentially decayed or exponential growth, with this imaginary part, which turns out to be sinusoidal.